Hi everyone, this is David Singletary. This is COP2073C, Introduction to Statistical Programming with R, and this is Module 7. In this module, we will start taking the name of the course a little more literally and actually doing some statistics with the R that we've learned so far. We'll have discussion of elementary statistics. We'll do a little more plotting, a little more visualization with our data, and we'll talk about probability and probability distributions. A lot of this will be review of the statistical concepts that you should be familiar with. There's two basic types of variables. We have continuous variables. This is where the range between two values is technically infinite. If we have floating point values, for instance, between 1.0 and 2.0, there's really no limit on the number of values in between those two numbers that we can specify using continuous variables. Then we have discrete variables. Each of these has a distinct numeric value. If we restrict our range of those numbers, for instance, we say we're only going to work with numbers between 1 and 100, then the number of possible values we have to work with there is going to be finite. We'll talk a lot about variables in our data, the categories of data in terms of the quantities of variables we work with, have the categories of univariate for single variables, multivariate for multiple variables, and we can split that into smaller categories. We have this bivariate, which is for two variables in our problems, and this is one of the more common ones we'll see, especially when we get into plotting, because we have a lot of two-dimensional plots we do on an x and y axis of two variables. Multivariate in general refers to just multiple variables. There's no real specification of the count. It's just more than one. And we need to distinguish between parameters and statistics for our terminology. Statistics is a derivation of characteristics of a population. The population is the entire collection of the test objects that we're working with, whether it's people or flowers or insects. When we do parameters for a population, we would be determining the characteristics of that population. One example is the population mean using the Greek letter mu, and we can calculate that for a population, but we typically don't work with the population. We want to extract data into a smaller subset of that population known as a sample, and so the derivation of those parameters are a little bit different, and they are intended to be representative of the population, but that's one of the things we have to verify, that the parameters we extract, which are called statistics, do actually represent a particular population. One example of a parameter for a sample would be a sample mean. Using x bar, we'll see it represented by that character instead of the full population mean. And there's a slightly different calculation we use to do this sample mean. So we start off with some summary statistics. This is doing just what it says. It's summarizing our data. There's various categories of summary statistics we look for. We have centrality, how the data is centered around a particular value, typically the mean, and then we have other measurements, the median, which is the middle value, versus the mean, which is the average. We have the mode, which is the data points that occur most frequently in a collection. And we also have range, variance, and standard deviation, looking at how the data is spread out. We have counts and percentages. This is for categorical data. So when we're looking at, for instance, political competition, where you would have political parties, and those would be categorical variables. Then we have quantiles, percentiles, and then we have covariance and correlation, which is where we look at two variables in the sample and try to determine the strength of the relationships between them, if there is one. So we're going to look at some examples here for the summary data. There's a neat little study on the web evaluating pumpkin varieties in the southeast, done by University of Tennessee. So here's a screen snip of some of the data they collected, and you can see we have various categories of pumpkin sizes, and then we have the name of the type of pumpkin, the nickname, seed company that provided it, the total weight per acre. More data here. We're going over here to the far right column, the average weight per fruit. This is in pounds, and we're going to extract this data for the medium size category of the pumpkins, and we're going to do some summary data for this little subsection I have highlighted here. If you want to look at the study, here's the website for it where you'll find all the data. First thing we'll do is we want to represent the data as a vector, and we just put the table data in here manually and assign it to this vector called weights. Then we can calculate the mean. Remember, the mean is another name for average. We use the mean function and pass that vector to the mean function. We have the median. This is the middle value, and we use the median function. past weights to it. And then I'm just using the cap function here to display those values. Here's the mean of all these values in this data vector, and here is the median value, the middle. We can calculate the standard deviation. This is the distance from the mean, and we see 3.26 is the standard distance from this mean of 19.56. We can calculate the range. This is the difference between the smallest value and the largest value to see the minimum and maximum points that we're working with in the data. So we just use the max value found in this weights vector and then the min value found in the weights vector and assign it to this variable range. Now for the mode, which is the most frequently occurring value in the vector, we don't have a function that we can do this with directly in R. There is a mode function. If you look it up in the documentation, you'll see it returns the storage mode of the data, which isn't relevant to the statistical mode. But we can write a function of our own pretty easily, and there's a lot of them on the web. And if you look at most of them, they work in a pretty similar fashion here. They look at the data and find a vector of the unique values in that data. If a value occurs twice in the vector, they're only going to list that value once. Then they get the count of the index values for each unique value. So they look at how many times each of those unique values occurs in the original data vector. Then they find the maximum number of indexes that occur with the values, and that's going to be the index of the mode value. And so they find that maximum value, and then they extract the element value from the original data vector, and that's your mode. So this little function get mode, we pass it a vector v, we get that unique vector. If there's no unique values, if they're all different, it'll be the same size as the original data. But if you look at our original data here, we do have a couple values that occur twice at the very beginning, 23.7. So 23.7 will only occur once in this unique vector that it's creating, along with all the other values. Then it gets the index values of the unique values in the original data using the match function, and it tabulates them, which means it counts them. So it gives us a vector of counts of each of those indexes, and then we use this which.max. Remember the which function? Well, which.max is a derivation from the which function that will find out the maximum number of values in this tabulate result. And the maximum value is going to refer to the element that has the most frequently occurring value in the original data, and that will be our mode. Now, in the last module, we talked about using the apply function, being able to efficiently apply a function over a collection of data. And I mentioned there's several versions of apply, several different flavors. The tapply is one of these. Tapply is useful for applying summary statistics in a group mode. Let's say we have groups of data based on a factor in a data set, and we want to calculate the summary statistics for each group. So in this example, we're taking the MT cars data set, which is a very commonly used data set in base R, and we are indexing it or grouping it by the cylinders. The summary function we're applying is the mean function. This goes through all the data and finds each group of data based on its cylinder value. So here we have 4 cylinders, 6 cylinders, and 8 cylinders, and then it calculates the mean within each of those groups. So we can apply this to our pumpkin data. There's a CSV file containing a select group of data from the full pumpkin data set that's available in the Canvas module, pumpkin.csv. And if I read that in using the read.csv function, assign it to pumpkin, I get a data frame, and I'm going to change the names because the names of the actual data set are kind of messy. There's a lot of embedded spaces. So the columns I'm going to get are the size of the pumpkins, number of immature pumpkins per acre, the percentage of immature pumpkins per acre, and then the average weight, which is the partial data set we already analyzed. So in this data set, we have multiple groups categorized by the size. Here's our medium grouping. We also have giant, extra large, large, small, and mini. And so using tapply with the average weight and specifying the size, which is the category based on giant, extra large, large, medium, small, or mini, and then the mean function calculates the mean for each group. So here's our mean calculation from the previous slides, and then we have for each of the other size categories the mean values for those groups as well. And then here we're using tapply to apply our custom mode function to that data set and get the mode for each of those size groups here. So you can see tapply can be very useful when we want to analyze multiple groups within a single data set. Quantiles are a measurement tool that allows us to place observations in a certain quantitative category. The median that we've looked at already is at the 0.5th quantile. There's no real limit to the number of quantile groups you can come up with, but they're normally specified with 5 values, starting at a minimum value, and then a maximum value, and then these 4 groups. And we most often refer to them as percentiles. We take that fractional value and convert it to a percentage. And so you see here, running the quantile function in R with our pumpkin weights, we get a 0% through 25% quantile, and observations will fall somewhere in that range. And then the 50% quantile, this is our median, and then 75% and 100% for the maximum value. We use box plots to visualize quantiles. They're also known as box and whisker plots. They are typically in, again, that 5-number summary. The function is pretty intuitive here. You see we're calling box plot, providing the average pumpkin weight, and then we can specify different options. By default, you get a vertical box plot. So I've flipped it here to fit it better on the slide to show a horizontal box plot instead. And then you can specify a range. A 0 range shows the extent of the data all the way out through the highest and lowest points. If I didn't specify this range, we would see a lower maximum value, and R would be trying to categorize that high level. If we go back and look at the data here, 64.3, R would be putting that 64.3 out here as an outlier that's outside of all the data. But by specifying this range equals 0, it stretches the maximum all the way out to its highest extent here. These dashed lines are the whiskers of the plot when it refers to a box and whisker plot. And then this first vertical line is the 0th percentile, and the right vertical line is the 100th percentile. And then we have the 2 boxes here. The left side of the left box is the 25th percentile. Here's our median value, and then here's the 75th percentile. So if we looked at the data in terms of the numbers, we would see that most of those values are falling somewhere in the middle here. And then you have the more extreme values over here on the whiskers. Another summary stat we can look at is the variance. This is the distribution or the spread of the data, how far it is from the mean and how far the points are from one another. If you have a variance of 0, that means all the points are the same. R gives us the variance function, VAR, which calculates the sample variance. As you get bigger and bigger samples, this approaches the population variance. Examples here, we're using the weights vector, our medium category pumpkin weights, and the variance of that vector is about 10.5. If we look at the variance of the entire distribution of the pumpkin weights, you see we get a pretty high variance value of 200 and almost 231. So the higher the value, the more variance or the more distributed the data is. The dirty little secret of the variance function is that all it is the square of the standard deviation. If we do this calculation where we take the standard deviation of the weights vector, and if we square it, just multiply it by itself, you can see that is the same result as running the variance function with that weights vector. See, we get the same result. So this is a different way to use the standard deviation to produce another quantitative measure of your data. Now, this is more useful if you visualize it. So if we look at a plot of the data, if we plot it on a horizontal line, and we provide a incremental x-axis, and then we look at the maximum possible values. Just to do an apples-to-apples comparison here, I'm using 0 to 65 for the y-axis to cover the outlier of the full data column that we have for the pumpkin weights. And so using this plot for the weights vector, you can see with that variance of 10, everything is pretty much clustered around the mean. It's fairly close. Whereas if you look at the entire distribution of all the weight data, including that outlier up here, we have a pretty wide variance. Now that outlier is definitely impacting the variance of the data. If we go back and calculate the variance of that full column minus that outlier, so here I'm going to say pumpkin, and we're looking at the average pounds, and I'm going to subset. If I look at the data here, that outlier data is the first element in this list, whereas you have another one of these giant categories that's at a lower weight. So if I want to exclude that outlier, I'll just do a range of elements 2 through the maximum value, the maximum element here, which is 26. And you can see I get 165 for the variance instead of that larger value of 200 and almost 231. Covariance and correlation are two summary stats that we use to examine the relationship between two variables. Covariance describes whether there is a relationship or not, more of a yes-no question. We'll get a positive value that indicates there's a positive relationship. In other words, as one variable increases, the other also increases. There's a negative covariance where a variable increases and the y variable decreases. And then a covariance of 0 indicates that there's no relationship. Now you'll get different numeric values for this. You're really just looking at the positive, negative, or 0 result. To get a measure of the strength of the relationship, that's where we use correlation. So R gives us this COV function for covariance, and then a COR function for correlation. As an example, if we run the covariance function on our pumpkin data using the percentage of immature pumpkins found in the sample to investigate whether it has an impact on the average weight, overall we get a covariance value of 59. And again, the numeric value that we get for this value isn't as important as whether it's positive, negative, or 0. So this indicates that there is a positive relationship. Now to examine the strength, we run the correlation function, COR, with the same data, the two variables, percent immature and average weight. And you see we get a 0.29 value. So values between -1 and 1 indicate the direction of the relationship as well as the strength. And the 0.29 is about a fourth of the way up on the positive relationship scale. So it's a fairly weak positive relationship between the two. If we plot these points, you'll see that on the x-axis, as the x-axis increases, the y-axis value more or less increases. If you look at this cluster of points here, you could probably interpret an upward slope through those points. But just looking at this in terms of the plot is more or less like a Rorschach test, or identifying shapes in clouds. It's not really precise, and so we look at the numeric value to give us a better indication of the strength of that relationship versus trying to interpolate lines through a set of points. Now, if I run the covariance and correlation functions on a subset of our data, in particular the medium pumpkin category size, we see that the relationship increases a little bit because the subset of data is not as dispersed as a full data set. So here I've extracted the medium category pumpkin data from our data set for the percentage of immature pumpkins found. It is rows 10 through 20 of our data frame that we read in for the CSV file, column 3. And then I'm running the covariance function with the percent of immature pumpkins on the x-axis or for the x variable, and then the weights for the y variable. You see we get again a positive covariance value, which indicates there's a positive relationship. And then if I run the correlation function with the same data, I get a much stronger indication or measurement of the positive relationship here. We're up halfway on the scale from 0 to 1 for a positive relationship. And if we plot this data, you can see now that you definitely have a higher trend going through the points that would indicate the positive relationship. It's still hard to discern if you just look at the plot, though. That's, again, why we want to run the correlation function. Now, if we had a positive relationship of 1, it would be a perfect diagonal. And the relationship of -1 for the correlation, it would be a perfect downward diagonal for that. So you can see we're about halfway in terms of the slope of a trend line going through those points. Here's an example using the MT cars data set that we looked at previously. This is measuring the miles per gallon per cylinders for the cars. This is a kind of a special case of running these functions on this data set because the cylinders are more like a categorical variable because you don't have a continuous spectrum. It goes 4 cylinders, 6 cylinders, and 8 cylinders for this data. But it still does calculations for us, and it comes up with a negative relationship for the covariance function, which means as the number of cylinders increases, the miles per gallon goes down, and that would be a pretty intuitive result. Correlation gives us a fairly strong negative relationship here. It's almost -1. Then if we plot the data, you can see our cylinder data causes the points to line up in these vertical lines on each set of 4 cylinders, 6 cylinders, and 8 cylinders. There's pretty obviously a fairly strong negative relationship that you can draw this negative line down through to visualize that. So here are a bunch of examples of correlation values just to show what the plots look like. Here's a -1 relationship. Here's a -0.8. So you see you get more scattered, but there's still a pretty strong interpolation of a line going through those points. -3, not so much. This has a lot of variance in the data. And then positive, now we're going up with a moderately sloped line and then a steeper line. And then for the perfect relationship or perfect correlation value of 1, is a perfect upward diagonal. And then you have these cases of a correlation value of 0, where it's just a bunch of scattered points and we really can't discern anything from that in terms of a line, or something like a sine or a cosine wave that is just regularly going up and down, and so you can't really draw a directional or a diagonal line through those. And then you have a lot of scattered groups of data here where you can't come up with a relationship between those as well. So these are used to examine and quantify the relationships between two variables. I've been mentioning outliers. Outliers are the extreme data, the things that don't fit with a group of data. That value of 64 for the pumpkin weight was an example of an outlier. The outliers can happen naturally, where it's an actual observation that's been recorded. That pumpkin weight would be a natural outlier. Or if somebody messes up an input value, that would be an unnatural outlier. Typically, when we do analysis, we eliminate the unnatural outliers if we can identify them. But whether to include them in a data set for the natural outliers is a tough decision sometimes. They will definitely impact your calculations, but they might be very relevant to the data and they might need to be taken into consideration. The decision to include them or not really comes with detailed analysis and experience. We definitely want to identify them in general, and a lot of times we'll present an analysis both ways. One result includes the outliers and another result excludes the outliers, just so that we can compare, disclosing as much as possible to show that we're not trying to skew the results by hiding the outliers. Now let's do a little bit more with visualization, add some more plotting tools to our toolkit. We've seen line charts and scatter plots, and we looked at box and whisker plots. Bar plots are another popular visualization mechanism. We can do categorical data with this, typically by frequency, how many times a category occurs in a set of data. We also have an alternative of a pie chart. Bar plot can be horizontal or vertical. Let's look at an example which plots the frequency of the cylinder categories in the empty cars data set. Here I'm just showing a subset, the first 5 rows. We have the third column here which lists the number of cylinders. And so if we look at the empty cars data set as a whole, we're going to use the table function to create a table of the frequency of each of those categorical cylinder values. So all the table function does when we pass the cylinder column to it is it says, I found these distinct categorical values for the cylinders in the data. There are this many in each of those categories. So we have 11 4-cylinder cars, 7 6-cylinder cars, and 14 8-cylinder cars in the data. And because a bar plot is going to plot our frequency, it's very intuitive just to call the bar plot function and pass this table to it. And it takes those categories, puts them on the x-axis, and then the frequencies are our y-axis. So we see the 11 4-cylinders, and then the 7 6-cylinders, and then the 14 8-cylinders. Now, if we have a simple bar chart, for instance, a vector, we need to provide a little bit more information. So here is a monthly rainfall amount in the form of a vector, and there's 12 values here, so we can associate the names on the x-axis with a name vector, which here is the names of the months, or abbreviated names of the months, and then we call bar plot with the vector. We pass that month vector using the names argument, and you see it puts the names of the month under each of the categorical values for that rainfall. And we'll typically want to jazz it up even more, make it more attractive and interesting to look at. So we have options like specifying the x-axis label using the x-lab argument, y-lab, then the limits for an axis. For the y-limit, we can specify a vector for a start and end value, and we can specify a color. And so here we're calling the bar plot with that rain vector. X-label is month, so we're putting a label on the x-axis down here. And then our Y label is rainfall in centimeters, and here's that argument. We're going to specify the range of our Y-axis here, a vector containing the low and the high end, and then we're using a light blue color for the data bars. We can also add attributes to our plot. So here we're putting cross lines on the plot at an increment of 2 starting at 1 down here. So we're specifying a sequence starting at 1, going through 9, every 2 numbers. Line type is 2 for a dashed line, line width 0.5, and the color for the line is the gray 40. And so you can see these lines showing up here going across, just to help us visually interpret the values. And then we can run a box command that will draw a box around the plot. So you notice each time we execute one of these additional functions after calling our first bar plot command, it incrementally adds attributes to that plot. The stem and leaf plots are a textual tool that helps you visualize the distribution of your data. So they call it a stem and leaf plot because they take a list of values and then they have a base or a stem using, in this case, they're using the first digit of each value. So you see you have 15, first digit is 1 in the tens place. 16, first digit is 1. So the stem for those two values is 1, and then the first value, the leaf, is 5, which represents 15, and then 6, which represents 16. This gives us a quick way to look at a textual format that tells us that we have this many values that are somewhere in between 10 and 20. And then we look at the 2's. We have a 2, 1, 2, 3, 2, 3, 2, 6, 2, 6. So you have 2, leaf is 1, leaf is 3, 3, 6, 6. So we have 5 values that are in the 20s. And then we have 2 3's, 2 30 values. Leaf is 0, leaf is 2 for these two numbers. And then that single value in the 40s, and it's 41. Here's another example. A statistician for a basketball team tracks the number of points each of 12 players has in a game, and then they use a stem and leaf plot to show the data. So here are values 0, 0, 2, 4, 7, 7, 9, 11, 11, 13, 18, 20. So our stem for the 0, or the values that are less than 10, in other words, we have 2 zeros, we have a 2, we have a 4, we have 2 7s, and we have a 9. And then for the 10s, that's here and here, we have the stem is 1, here's 11, 11, 13, and 18. And finally, we have a single value in the 20s, and that is 20. So R gives us this stem function, and we're just using a random set of data here, a random vector of data. And this is what it looks like when we run with R. R's set up to show us floating point values, values with decimal points. So it's telling us here the decimal point is at the vertical pipe. Well, there are no decimal points. This is all integer data, so everything that follows that vertical pipe in this example is going to be a 0, but that's okay. We'll start with a stem of 2, and you see we have 1, 2, and then we don't have a 3 here. So this is a way that R is collapsing the representation of the data to show it in a more compressed form. The 3 is represented by this stem value of 2. So in other words, it's creating kind of a container or a bucket to contain all the values between 2 and 4, not inclusive of 4. So we have a single 2, and then we have a 3 here, and a 3 here, and a 3 here. So we have 1, 2, and 3 3's, and that's represented by these 4 zeros here. So we're not going to see a stem of 3 in this particular example. Then we jump to 4, so how many numbers do we have between 4 and 6, not including 6? We have 2 4's and 4 5's, and so you see we have 6 total values there. And then here's the bucket for 6 and 7, and the bucket for 8 and 9. Now these are actually called bins. And in fact, we can increase the number of these bins, and we'll hear about bins a lot in a lot of the visualization stuff we do in R, and the process of binning or categorizing data in buckets or bins as they call them. So with this data set, if I specify a scale of 2, I'm going to double the number of bins. Now I get my stem for each individual value, so it breaks it out. The idea here is R is trying to save us space because this, again, is a textual format. It doesn't want to have us have to do too much vertical scrolling, so it compresses it this way by default. But we can get a more comprehensive view of our data. So this example with a scale of 2 is increasing the number of bins, so we'll get a stem for each individual value. And so we have 2 7's in our data here and here, and so we get the 2 zeros following this vertical pipe for the stem of 7. Now we get into the use of real numbers or floating point values. So here's another vector with floating point values that have some 0 significant value and then some with fractional values of 0.5 and 0.5. Well, it looks like they're all 0.5 or 0.0. So here's how the stem and leaf breaks out using the stem function in R for this. We're going to use a scale of 2, but you notice we're still going to be skipping because now we have more values in our vector. This vector is bigger than the previous one, so R still kind of compresses it and doubles up on the values represented in each bucket or each bin as shown by the stem. So we have a stem of 8, so find the numbers that start with 8 in this vector. We have this one here, and now because we're a little compressed in this representation, find the ones that start with 9. So here's 9, and here's another, and they're both 0.0. So after the decimal point, the vertical pipe will see 0. So we have 3 values that have a value of 8 or 9, or in this case, somewhere between inclusive of 8 and less than 10. We're just simplifying it with 0.5 to show this example. So we have 10, and if we find a 10, there are no 10s, but there are 2 11s, and so we get those 2 11s represented here. Now we get into the non-zero fractional values. So our stem is 12. We have 12.5, 12.0, and then 12.5 again. So here's how R is representing this. Now it's not doing them in order, it's just using the lower leaf value first. So 12.0 comes first, even though this 12.5 comes before it. And so it's doing it in numerical order. And so 12.0 and then 12.5 and 12.5. 14, what do we have for that? We have, here's a 14.5 and here's a 14.5. Nothing else between 14 and 16, so we see those two 14.5 values. And then there's nothing for a stem of 18, and we start up again with 20, where we have a value of 21.0. To graphically represent continuous data, we want to use histograms. This is an example of the histogram of the horsepower values from MT cars, and we have these bars which represent a bin that count the number of occurrences within that range of values, between 50 and 100, for instance. Notice the difference between this and a bar plot, which is here, where we're showing the horsepower values as categorical variables. In other words, we see each value that occurs in the horsepower data here. It gets its own bar, and we get the precise representation of that, whereas a histogram can get more than one value within a particular range in a single bar. So just like we did with stem and leaf plots, we have bins and histograms. The size of the bin is known as the bin width. As an example, here is that horsepower plot again in a little larger format so we can read it more easily. And you see the width of these bins is 50 units, where a unit is 1 horsepower. And then we have up to 350, and we can see that up in the higher ranges we don't have that many of the high horsepower values. And we also look at the shape of these histograms. We'll get into distributions in terms of normal distributions and other different types of distributions. So for a normal distribution, we're looking at a bell shape. But you can see this one is not bell-shaped. This is known as a right or positive skew because we are tapering off to the right. Depending on the size of your bins, that shape can vary. So here we have a bin width of 50 units by default. We haven't provided any other values to this hist command, which plots the histogram. If we modify that using the breaks argument, so here we're specifying a range of 0 to 400 for the continuous data range, and we're specifying a bin width of 25. And so look at the difference between this histogram and the one on the previous slide. We now have 4 slots, if you will, or 4 bins for values from 0 to 100 in increments of 25, and it goes all the way up through 400. So now the shape is a little different. It's still right skewed, but now the center is a little higher, and we see we have some lower values on the left side that we can take into account. So this is how we modify that bin width, is by using this breaks argument. We have other things we're doing here. We're showing a vertical line for the mean and for the median here, and providing a legend for the histogram. And those are just enhancements to the chart. The basic histogram we're showing with this range of bins and this color, and then the title, and then an x-axis label, whereas the frequency is a default label that R applies for histogram because that's what you're measuring. So let's do some histograms with our pumpkin data. We have the weights vector, which is the select category of the medium weights from the data. And you can see we get a range from 14 through 24. And so these bins, again, are representing the data that falls into the ranges from 14 to 16. We're not looking at individual values, but We're looking at the observations that fall within that range of values. We can set breaks to change the bandwidth. Right now you can see it's about 2. Let's go down 1. Breaks equals, now this is a sequence. This isn't a vector. So make sure you do the right function here for this argument, the sequence, and let's go from 12 to 26 and specify 1 for our bandwidth. And you see now we get a much more granular look at the values in that vector. Now the x-axis labels are just going to be set based on the size of the chart. You can see if I increase the width of this chart, I get more x-axis labels in there. So those aren't necessarily representing the actual bandwidth. You wouldn't want to look at here and say, oh, my bandwidth is 12 to 16, so it's 4, because we know that it's 1. And so don't be misled by the x labels for this. Our bandwidth here is 1 unit, or 1 pound. We can chart our entire data set, hist, pumpkin, and go with the average weight across the whole data set. So here's our histogram here, 0 through about 65. Our bandwidth looks to be 10. So this is 70. So you see we have that outlier value occurring up here, and it's including that. And you can see it skews the shape of our chart. We have a definitely right skewed chart here as well. Now if I specify a range for our breaks, and I will do sequence, and we can see we've got some low values here. So I want to do 0 for my low end of the sequence, and I'm going to go to 60 on my high end. It's not going to include that outlier, just to show you what happens here. So 60, and then let's just go with 5 for our bandwidth. And you see now that it doesn't do it. It gives us an error. It says you've got some values that are not being counted. Your breaks should span the range of x. So it's not happy with that. So let's fix it, and let's provide the additional 5 pounds there so that that outlier does fall within the range. And then it's fine with that. It plots our histogram, kind of awkward on the x-axis label here for that tick, but you can see it does include the outlier here on the very end. And you can see that now we can actually see that there are some low values on the left end as well. Now let's move into some more statistical theory, talk about probability. We'll do a little bit of background here first. Most of this should be review for you based on the Introduction to Stats prerequisite. And then we'll talk about how we do probability in R. One of the major goals of statistics is obviously calculating probabilities about things that are going to happen. The formal definition of a probability is a number that describes the possibility that something's going to happen or not based on one or more observations. It's always a number between 0 and 1, inclusive, and it's usually expressed as a fraction. To calculate probability, we need to have an event. So an event is an outcome that can occur and that we can measure, and then to describe the chance of an event happening, we use the probability, abbreviated as PR, of an event A. And if the probability of an event is 0, that means it can't occur. If it's 1, that means that it will definitely occur. And then all the various fractional values in between. Simple example, let's roll a 6-sided fair die. Now I'm thinking that statisticians must have had some bad experiences in the casinos because they always insist on a fair die. And so that propagates into these types of descriptions. So a 6-sided fair die where you have the numbers 1 through 6, we're going to define the event A as you either roll a 5 or a 6. So in other words, there are 2 sides of that 6-sided die that you're going to be calculating the probability of. So it should be pretty intuitive that with a 6-sided fair die, the chance of any one side lining up is going to be 1 out of 6 when you roll it. And so we can define the probability of that event A, where we're rolling a 5 or a 6, as the probability of a 5, which is 1/6, plus the probability of a 6, which is 1/6. If we do the addition of the fractions here, we get a probability of 1/3. As an aside, this is a classical probability calculation where we're doing observations independently versus a Bayesian probability where we are using prior knowledge. That is a different category of statistics. For instance, if we're calculating the probability that we're going to sell ice cream on a hot day, we know where we have prior knowledge that on a hot day, ice cream is probably going to sell more than it would on a cold day. And so that would be an example of the Bayesian probability calculation. When we work with multiple events, we can start with simple independent calculations. If we have 2 events that we want to calculate the probabilities for instance, event A is you roll a 4 or more, a 4, 5, or 6, and event B is you roll an even number, a 2, a 4, or a 6. If these are two independent events, then we just calculate them separately. The probability of A is 1/6 plus 1/6 plus 1/6, which is 1/2, and then B is the same, 1/6 plus 1/6 plus 1/6 for the even number probabilities, and that's also 1/2. These are independent probabilities. When we get into conditional probabilities, that's where we have to start looking at combining these calculations. So a conditional probability is probability that something happens after something else happens. So we state it as the probability that A occurs given that B has already occurred. If you reverse it, then the probability that B will occur given that A has already occurred. If the probability that A occurs after B has occurred is the same as A occurring independently, then the events are independent. There's no dependency of the second event on the first. If the probability of A occurring after B occurs is not the same as A occurring independently, then the two events are dependent. And the commutative property doesn't apply to these calculations for conditional probabilities. You can't assume that the probability of A occurring after B has occurred is the same as the probability of B occurring after A has occurred. If we look at our dice example, let's look at the combination of the probability of A occurring after B occurs, where A is a roll of 4 or more after an even number has rolled. In other words, a 2, 4, 6. So given that we have 4 or more, that means we have 3 numbers to look at. An even number from those 3 values is going to be 4 or 6. So there's 2 out of the 3 that would result in a successful event for us. So the probability of 4 or more after we rolled an even number is 2 out of 3. The probability of A occurring after B occurs at 2 out of 3 is not the same as the probability of rolling 4 or more independently, which is 1/2. So these two events are dependent. We can simulate simple probabilities using the sample function. We touched on this function briefly in Module 1. If you look at the help page for it, you see that it allows arguments of a vector or a number of elements, then a size, and then this replace argument. R does a random shuffling of numbers by default with sample. This replace argument allows us to disable that so that we get the same sampling sequence in every execution. As an example, if we run sample and we want to take 6 values, and this is just the numbers 1 through 6. We want to take one sample from it, and we'll specify replace equals true. We get a 1, and if we execute again, we get a 4, and continue. So you see we're getting sampling similar to rolling a single die. Now to make it more interesting and to show the 1/6 probability that we talked about earlier, let's do more than one sample. Let's take, with the 6 values, 10 samples. We get these results, and let's say we're looking for a 6. So we have 1 out of 10. That's a little less than 1 out of 6. Let's try a bigger number. Let's go with 100 samples. And now, since it's getting really too big to count them, let's assign this to a variable, s sample 6 100. And then let's do a conditional subset here, s, where s is equal to 6. And then let's get the count of those using the length function. You see we get 15. So now that's 15 out of 100. 15 divided by 100 is 0.15, whereas 1 divided by 6, which is our calculated probability, is 0.16. So we're pretty close. So we would expect that the more samples we do, the closer to 0.16 or 1/6 we would get. Let's just try that with 1,000. And same operations. Now we get 162. And we're now at 0.162. So you see we're approaching that 0.166. So the more samples we do, the closer to 1/6 we'll get for that probability. Now that we looked at some probabilities, let's look at probability distributions. So distributions describe probabilities over a range of values. There's multiple shapes, but only one size. No matter how many values we calculate the probabilities for, the total probability will add up to 1. They're studied a lot. There's a lot of academic research, and so we have a good understanding of them. Most statistical packages provide a lot of support for them, a lot of features and functions, and R is no exception. We have 4 different functions that are associated with the distributions based on the distribution type. We have a D function, we have a P function, a Q function, and an R function. You can see the different purposes here for calculating the density or the cumulative distributions or the quantiles, random variate. We're not going to look at those, but we are going to look at the first 3, the D, P, and Q. And each of these has a name that is built from the distribution type. So for instance, for a normal distribution, we'll see a D norm function, a P norm, and a Q norm, and so on. And so these 4 functions are applied to the different distribution types, and they're specifically designed to do those calculations for that type of distribution. One basic distribution type is the Bernoulli. This is an either or. It's a single trial with a possible outcome of either success or failure with a calculated probability P, and P is between 0 and 1. And then we have the inverse, which is the probability of not P happening, and we refer to that as Q. And it's a very simple calculation of subtracting P from 1 to come up with Q. Other names for this type of distribution are binary or dichotomous. As an example, if we flip a coin, there's 2 possible outcomes. If we calculate the probability of heads, that should be 50% or 0.5, which means the value of Q, the opposite, in other words, rolling tails, is also 0.5. The possibility of rolling a 1 on a single die, as we've seen already, is 1 out of 6, 0.16. And Q is calculated by subtracting 0.16 from 1, and that gives us 0.84 as the probability of not rolling a 1. And then just a random example here of the probability of rain. If it's 20%, then the probability of it not raining is 80%. To plot a Bernoulli distribution is really simple. We just use a bar plot, 2 bars, one for the value of Q and one for the value of P. So in this case, the 1 represents the probability P at a 0.6% or 60% probability, which means that Q is 40%, represented by this bar with the 0. Binomial distributions are similar to Bernoulli, except they're designed for more trials. These are still discrete values, they're not continuous. If the number of trials is 1, then it's basically a Bernoulli distribution. If we have more, then we're going to get what we call a stair-steppy chart when we plot them out. And if we get enough samples, we're approaching a normal distribution, which is a continuous distribution that we'll look at in a few slides here. So here we're looking at a binomial distribution. So we've got this binary value that we're looking at 100 trials, and the probability of 50 successes is almost 8%. Now, if you calculated the area under this curve, you would come up with a value of 1. The area is equivalent to the probability. Remember, the probability under the entire curve is always equal to 1. If we have enough samples, you can see that it's very similar to a normal distribution here, which is a continuous distribution. Otherwise, you'll get this stair-step effect because these are all discrete values. For calculating binomial probabilities, if we consider multiple trials or multiple successes versus a simple Bernoulli probability calculation, if you don't have the formula off the top of your head, here it is. I don't want to do this. I'm going to use the D function for binomial probabilities, which is the D binom. You provide the number of successes, the size, in other words, the number of trials, the probability for an individual success, and then there's an optional log argument which interprets the result as a logarithm. We're not going to use that. The default is false, so we're going to just leave that out. So to replicate the Bernoulli probability, we call D binom with x of 1, which is the number of successes. So rolling any one number with a trial size of 1, and then this is our probability of 1/6, and you see this replicates the result. If we make these a little more complex and interesting here, for instance, what's the probability of 1 success with 2 rolls? This is using that formula I just showed you, but it's R doing the work for you, doing the heavy math, and so we call D binom with a success rate of 1 and a trial size of 2, and the same probability for 1 success, and you can see this is the calculated probability for this, and then a 0.3858 with a trial size of 4. How about 2 successes with 5 rolls? So that means x is now 2, and our trial size is 5. Same probability for a single success. So here's our probability there, and then 2 successes and 10 rolls. Here's our probability there. We can provide a vector for the x value for the successes, and here we're doing a vector with a range of 0 through 5, and you see it calculates the probability for each number of successes. So the probability of 0 successes, 1 success, which is the highest probability, and then 2, 3, 4, and 5. And we can plot the results using that vector. So here we are assigning the results of the function to x.prob, and it's a vector of probabilities. And then we just do a bar plot. And you can see here for the 0 success, 1 success, 2, 3, 4, and 5. So we can get a visualization of the probabilities for that scenario. The last distribution we're going to look at for this module is the normal distribution. This is one of the most common. You'd recognize it by a standard bell curve. We model continuous values with it. Another name is the Gaussian distribution. So here's an example of normal distribution plots with various parameters. The first one is the standard normal distribution with a mean of 0 and a standard deviation of 1. And this is the solid line here on this plot. Here's another example of a normal distribution with a mean of 4.5. So if you look over here, the middle of the curve is going to be the location of the mean, and then a standard deviation of 2. So you see this curve flattens out a little bit. It's not as steep. Another one with a mean of 0.5 with a standard deviation of 0.6. So this one you can see is much steeper. And then finally negative 3.3 for the mean with a standard deviation of 3.1. And so this is the flattest curve of all 4. Earlier we talked about variance. Variance is just the standard deviation squared. We can calculate z-scores using the formula of the variable x minus the mean divided by the standard deviation. We don't have Greek letters to use for our variable names in R. We can assign the calculations of these values to a variable and use the standard identifier as a variable, or we can just use the function names themselves. Here's an example where we have a vector x with 7 values, and we're going to calculate the z-scores for all of the elements in the vector. So we do the vector math here where we have x minus the mean function of x, so x minus the mean for each element of x, divided by the standard deviation of x. That's this formula here in a format that R can execute, and you see we get the z-scores for all of those elements. We also have a scale function which will do the same thing for us. If we have the same vector x here and we run scale of x, you see it gives me a list of those z-scores. Here is my mean value, and here is my standard deviation value. So this is a good summary function to run to do these kind of calculations for a normal distribution. So the dnorm function for normal distributions calculates density, not probabilities, unlike the dbinom function, which calculates the probabilities for a discrete value. So the function returns points that are calculated on a normal distribution based on the mean and standard deviation that you provide. This is an example where we're using the sequence function to provide a sequence of x values, and then use a dnorm function to calculate the corresponding y value points. And then we can plot the curve. So we're creating this vector x vals using this sequence from -4 to 4. We want 50 points. Then we're assigning the calculated y values with a mean of 0 and a standard deviation of 1. So the standard normal distribution. Here are our points on the x-axis. Here's our sequence function again. Here's our dnorm call, passing that vector. And then the plot, we pass the x values, the calculated y values, and then it's a line plot. And you can see here we get a bell curve. Our mean is 0, standard deviation is 1, and then we extend from -4 up to +4. The p function for normal distributions calculates a cumulative probability. So this is for calculating the area under the curve for a particular range. So we provide the rightmost value here as q. In terms of the standard deviation, And then the density under the curve starting on the right side is calculated. So here we go from 1 down to the bottommost range on the left side. So the probability of less than or equal to 1. And in this example, we're calculating the probability of values within one standard deviation. So to use pnorm for this, we'll do q of 1, and then we'll calculate the density under the curve for q of -1, starting at a standard deviation of -1 and working left as well. So we're isolating this portion in the middle by subtracting the pnorm of -1 from the pnorm of 1. That gives us the probability of all the values within this range for a mean of 0, and we get a total value of 68%. So a quick little word problem example. Widget weights produces weights that are normally distributed. Our mean is 17.46 grams. Variance is 375.67 grams. We want the probability that a randomly chosen widget weighs more than 19 grams. In other words, what's the probability that x is greater than 19? Now this one's a little bit tricky because they're giving us the variance. So because variance is standard deviation squared, we need to take the square root of that variation to use for our standard deviation in the equation. So we provide 19 for our q value. We pass the mean, and we pass the square root of the variance. So that gives us a probability of 53% for values that are less than or equal to 19. So to get the probability of x greater than 19, we just subtract that value from 1, and we see the probability of x greater than 19 is 46.8%. And finally, we have the Q function for normal distributions. This function works with quantiles. Given a value for a normal distribution with a specified mean and specified standard deviation, where will the bottom 85% of our values lie? So we provide 0.85 as a percentile, and this says that anything below this value will be less than the value of 73.1093. So in other words, 85% of the values in this population on this normal distribution will lie below that value. So let's just do a little check with this qnorm function. We'll go with the pnorm probability that a widget will weigh less than or equal to 19 grams. If we actually take the probability that was calculated for the pnorm function, in fact, let's go ahead and just plug this into R. So here's our probability that the widget will weigh less than or equal to 19 grams based on this normal distribution. And then if we take the qnorm and plug in that probability and provide the same mean and standard deviation, now we're using the same mean and standard deviation that we did in the pnorm function. And if we run this, you see that we get the inverse. It just calculates our widget weight based on that. So the calculated cumulative probability of the widgets being less than or equal to 19 grams is actually the quantile where the weights of 19 grams or less fall. So by providing that cumulative probability, we can calculate the inverse using the qnorm function.